means y is fixed. I differentiate x only. So I will not be using the product rule here. So I'll have 5x to the fourth times y to the fourth, and then plus 3x squared y squared. And that is fx. Now I can determine fxx. I'm differentiating the same function with y fixed with respect to x the second time. So 20x to the third, y to the fourth, plus 6x y squared. I can also determine fxy. So now I differentiate this with respect to y, keeping x fixed. So 20 x to the fourth, y to the third, plus 6 x squared y. Okay, and we have to determine, when we determine fyx, we have to get the same thing.
Wouldn't it be 20x cubed?
Okay, so let's do this again. So when I differentiate, when I found fx, y is fixed, right? So I only differentiate x, and I copy what's behind here, what's hidden here. So I have 20 x to the third, whatever, and then plus 6x squared, 6xy squared. Is that okay? Okay, now I differentiate this with respect to y. Four times 5, 20, whatever, times y to the third. 2 times 3, 6, whatever, times y. The whatever is x squared. The whatever is x to the fourth. See, these are my props. That's why I need my props. Is that better? So yeah, this says, okay, this says that take the first order a partial derivative of x, but now differentiate it with respect to y, keeping x fixed. Better? Okay. Now we want to find fy. So go back to the original function where I keep x fixed. I'm differentiating with respect to y. So then 4 x to the fifth, y to the third, plus 2 x to the third, y. I need also fyy, and then I need fyx. Okay. Fyy means keep x unchanged, differentiate this with respect to y one more time. 3 times 4, 12. X to the fifth, y squared. 2x cubed, when I differentiate y, I get 1, so I just get 2x cubed. Now, I differentiate this with respect to x, keeping y unchanged. 5 times 4, 20, x to the fourth, y to the third, plus 3 times 2, 6, x squared, y. They have to be the same. Any questions? Do you think that we should, I want to choose one problem with conditions, initial conditions. Maybe interdifferential in respect to, so tell me if you would like to practice more. Do we need to choose another?
Yeah, can you do one more?
Yes, please. You can choose anything you'd like from, let's say, 1 through 39. Pages 539, 540. Anything you like. Anything catches your eye or... before we look at a word problem?
Do you want to do the one with like the Greek symbol in it?
With lambda, for sure. Which one? Of course.
24.
Okay. So for 24, the only problem with this is that here we're only asked to find fx, fy, and f lambda. So this is a variable. This is a function. That's fine. X, y, lambda, and this is 9xy minus lambda 3x minus y plus 7. Did I copy this correctly? I think I did. Yes, I think I did. Good. Perfect pick. Why not? So we want to find fx. Let me distribute here. It will be easier. 9xy minus 3 lambda x plus lambda y minus 7 lambda. Okay, perfect. So we are keeping y and lambda fixed. We are only differentiating x because this is basically the f with respect to x. The first order partial derivative of function f with respect to x. So fx is, I see here x, so it's 9y. I see here x is minus 3 lambda. No x, nothing. Fixed. When I differentiate something fixed, I get 0. When I differentiate something fixed, I get 0. Any questions so far? Okay, so let's differentiate with respect to y. Is there a y here? Yes, so 9x. Is there a y here? No, gone. Is there a y here? Yes, so plus lambda. Is there a y here? Nope. Finally, f lambda. Is there a lambda here? Nope. Is there a lambda here? Yes. So negative 3x. Is there a lambda here? Yes. So then plus y. Is there a lambda here? Yes. Minus 7. Any questions? Of course, we can continue, but these are really not. Tell me which other combo you want to determine. You can say fxx, you can say fxy, you can say fyy, you can say fx lambda. You can say anything. So we can create at least one. We're not asked to do that, but since we are here, let's determine one second order partial derivative. Which one? See, for example, if you say f lambda lambda, it's going to be 0. There's no lambda here. If you say fyy, it's the same. There is no y, so it's 0. For example, if you say fx lambda, yes, it's negative 3. Okay, so let's look at a word problem to see how this works. And then there is only one item left that I would like to look at tonight. Finding the max min of functions with 2 variables. Okay, I'm looking for a problem. Okay, so let's look at 42. Is this okay? Did you want to look at other problems? When we get to finding max min, we're going to do this a lot in the next section, last section of the semester. So we're going to have a lot more in the next few minutes. Okay, so we're given a function. So this is 42 on page 540. that is P of X comma Y, and this is 2400 multiplied by X to 2/5 multiplied by Y to 3/5. These are not very friendly functions, as you see. P is the number of units produced, and X is the number, so P units produced, X is units of labor, and Y is units of capital. Okay, so find the number of units produced with part A. So P of 32 units of labor and 1,024 units of capital. It's very clear. All I have to do is evaluate. Let's plug it in. So 2400 multiplied by 32 power, I would put that in parentheses, and then multiplied by 1024 caret and put that in parentheses, 3 divided by 5. Let me make sure I entered everything correctly. Yes. So 614,400 units produced. Part B. Find the marginal productivities. So marginal productivities of course they're partial derivatives. So they are Px and Py. So when we keep the units of capital fixed, we differentiate with respect to X. So 2400 multiplied by 2/5 times X to power 2/5 minus 1, which is negative 3/5, and Y to 3/5. I will try to simplify it a little bit. So when I simplify by 5, what do I get? So I get 480. Yes? And then I multiply by 2. Let's say, what do I get when I multiply by 2? 690. And X to negative 3/5 and Y to 3/5. This is the marginal productivity for the units of labor when we keep the units of capital fixed. Okay, P, Y. I will differentiate with respect to Y, keeping X fixed. So then 2400 multiplied by X to 2/5 times 3/5 times Y to 3/5 minus 1, which is negative 2/5. I will simplify again. I get the same thing, 480, but this time I have to multiply by 3. Am I correct? 4 and 2, 12, 4, right? 2 and 4, 4 and 2, and 12, 12. Very good. So X to 2/5 and Y to negative 2/5. So we determine the marginal productivities. Evaluate the marginal productivities at the same values, 32 and 1024. No problem. All I have to do is just plug it in. So Px evaluated at 32, 1024, and Py evaluated at 32, 1024. Okay. I will directly plug it in. 960 multiplied by 32 caret, in parentheses, I have negative 3 divided by 5, and then I have 1024 caret, and the power is 3/5. 3 divided by 5. 7680. Next one. What do I have? I have 1440 and then times 32 raised to power 2/5 and then multiplied by y, which is 1024, and the power is -2/5, 360. Any questions? Any questions? Any questions here? Finally, what I wanted to also accomplish today, so we can review for the final exam when we come back, we do not meet on Thursday, is section 6.3, and this is the last topic of the semester, max-min for functions of two variables. And they can have max-min, of course. And there is a technique, and it's called the d-test. And the steps for the d-test are, number 1, find fx, fy, fxx, fyy, and fxy, which is the same with fyx, as we know. Number 2, step 2, solve the system fx equals 0 and fy equals 0. Solve this system. Let's assume that a comma b is the solution, a solution, any solution. It can have more than one solution. So let's assume a comma b is a solution. In step number 3, that's why it's called the d-test, find d. Okay, what does d equal to? It's fxx evaluated at a comma b multiplied by fyy evaluated at a comma b, and then minus fxy evaluated at a comma b but squared. So before we continue, we find all the partial derivatives, first order, second order partial derivatives. Then we create this system only with fx and fy. So we set them equal to each other, set them equal to 0. We solve the system. We determine solution or solutions. If these are kind of critical numbers, right? From functions of one variable. Then we determine this number. This is a real number. It could be positive, it could be negative, it could be 0. So there are 3 possibilities. Okay. If d is 0, the d-test is not applicable. If d is a positive number, that's one possibility. And if d is also positive, if d is negative, so there's another option. So if d is negative, this is a saddle point. In other words, no max-min. But there are 2 options for d being positive. And fxx evaluated at ab is less than 0. If that's the case, the function has a max. If d is positive and x at a comma b is less than 0, is greater than 0, sorry, then this is a minimum. With greater than 0 is a minimum, with less than 0 is a maximum. But D must be positive. If D is negative, no max min. If D is positive and fxx is negative, then it's a maximum. If D is positive and fxx is a positive, then it's a minimum. So let's start with a problem, and then we'll look at an application. On page 547, so let's start with an application. With the numerical situation, just a function, and then we'll look at applications, or we can go directly to applications. The method doesn't change. It's exactly the same thing.